I want to talk about planning in an ambitious way, planning with approximation, planning that reaches more towards all the kind of reasoning and thinking, more cognitive things that we do. And also, I also want to bring it right down to the equations and the Markov decision processes. So planning, it's AI's way of talking about these larger goals about cognition, reason, thought. Now, in reinforcement learning, planning is more like dynamic programming with a learned model. And it's challenging to do this with genuine approximation in the model. The hard-seeming aspects of planning are straightforward. It seems to me, things like partial observability, temporal abstraction are relatively straightforward. Average reward, I'll talk about those. But just the basic planning step of doing it approximately, I find to be the most challenging bits. So this is just sort of summarizing my points of the talk. But part of the aim is to do all these things in a general, scalable, and computationally manageable way. And it's trying to pull all those things together that makes it hard. It's hard, and yet something like mechanical reason, I think, is within our reach, and we should strive for it. So how can I, with these grand goals of relating to knowledge and thinking, how can I get started? How can I find a common way of talking that we can all use? So I think a good place to start is with this idea that the mind has two parts. A fast part, it's like how we immediately react to things. Maybe they're learned, but they're just reactions. They're not considered. And then a slower, deliberative part that makes better choices more slowly in the long run. And that slower, deliberative part is what we're talking about when we're talking about planning. So you've probably heard me in other talks talk about the foreground and background of the mind. The foreground is the things that are fast, running all the time. And the things are going on in the background. We're thinking about things, deciding what we'll do later. That's the planning, the deliberative part. And this is also popular in psychology. This Daniel Kahneman wrote this best-selling book, Thinking Fast and Slow, and he called them System 1 and System 2, and it was all about how you can think about the mind in these two ways. And in control theory and robotics, we also tend to think about these two steps. There's a controller that's running all the time, fast, and then there's planning for trajectories. So now in the classical model-based reinforcement learning way of thinking, and yeah, of course, I always think of this in terms of DINA. Yeah, Zoom puts up this little window that gets in my way no matter where I put it. I'll try to ignore it. So in DINA, we have our reinforcement learning algorithm. Let's just look at the picture, interacting with the world, usual inputs and outputs. And then if you want, you can replace the world with a model of the world. You swap it in the world's place. And you interact with the model of the world for a while, and you figure out what you would do if you, according to the model, and then you go back to interacting with the world. So you can learn, which is planning, from interacting with the model and behave better. So this diagram in the lower right shows the basic things that happen. We have experience, we have a policy, and the policy determines how we act, and then that generates the experience, and then that is fed back to modify the policy. And this is what's classic direct reinforcement learning, model-free reinforcement learning. But there's another path, there's a second path, where we can use the experience to improve a model learning. And then we can use the model to improve the value function in the policy. So that's planning. So we're talking today about this other path. And there are two steps to this other path. There's the model learning step and the planning step. Planning, to me, means just once you already have a model, or what you do with the model and how you use it to improve your policy. Planning does not refer to how you learn the model, though of course that's a very important part of doing it well, is to learn a good one and exactly how how it is learned and what is learned is at issue. Your different ways of doing it. Okay, so I hope everything on the slide is sort of familiar to this group. We know what a policy is. We know what a value function is. We know what a model is generally. And we know that planning is this process of using the model and computation, but no new data to improve its value function and its policy. I wish I could just get rid of this thing. I can't even move it now. So if there's something important on the bottom of my slides, you guys are gonna have to read it yourself. I have no idea what it is anymore. Okay, planning takes many forms, and other than what we do in reinforcement learning, they're all related. They're all really interesting to consider their variations. I just want to mention some of the things. You know, alpha beta tree search is a kind of planning, and Monte Carlo tree search is a different kind where you go down single paths to the end and do updates. Single agent search that is widely studied here by many of us, and dynamic programming as in value iteration. And they're all ways of using the model to improve the policy. And something else important that's on the bottom of my slide that I can't see. Planning by value iteration is the way we do it, the kind of dynamic programming that we focus on in reinforcement learning. And so let's just make sure that's 100%, because that's where that's the foundation on which I'm going to build. And this is an equation that we're going to see a bunch of times. I'm going to modify it. So let's take the time and understand this equation. So this equation is something that will be done at states. Like basically the process, there's an outer loop where you sweep through all the states many times. Like it's really two outer loops. You sweep through all these states, and at each state you do a backup. Okay, and this equation is the backup. And so the backup, well, it's not a bad equation. It says the value estimate of some state with it that you're backing up is computed in this way, and replaced. Value is replaced. I don't know. Maybe it's kind of fun to look at this picture first instead of the equation, because you know equations, you can get confused. I'll probably get confused explaining it. But here is the picture. The picture is here's the state at the top whose value we're changing. And then we're looking, oh, what are the different actions we might do? And then the world, what's the world going to do? It's going to choose a particular next state. So there's our choice, and that's where we're taking the max over our actions. Okay, and when we pick an action, we get an expected reward. R hat and P hat, those are on the model. Well, what is this model thing? Well, notice this picture up in the corner. The model, it takes in a state and an action, and it gives me a probability distribution over the next state, and it gives me an expected reward. I'm going to call those R hat and P hat. Those are the two parts to the model. And I used to have a thing that pointed to this part and said, this is the expected reward given that I've done this action in this state. Okay, the expected reward, this is the model. These two red things are the model. And then this is the transition probability. How probability of my ending up in S prime, given that I've in state S and I've selected action A. So you know, I'm basically trying to decide which action is best. And so for each action, and I'm going to action A, the value of the best action. So the value of the best action, I have to take into account the reward that I'll get and the value of the next state discounted by gamma, a number like 0.9 or something. And yeah, so these branches correspond to branches in the equation, and this should be pretty familiar to us by now. And really, every planning method involves this step, this elementary backup step. And they just do the backups in different orders. Like if you're doing Monte Carlo tree search, you zoom down a narrow path, and you're doing something that is like this or is approximating this. And in different kinds of tree search are also doing that. So I'm going to have us now just focus on value iteration because it's good for reinforcement learning applications, and it's typical of many planning methods. So now within this context, I'm going to look at 5 challenges. This is like an outline of the rest of the talk. So the 5 challenges are 5 extensions to value iteration to make it more realistic and powerful. There are also 5 major branch points in research directions, different ways we could go, or you could go, people could go in their research. So these are also 5 challenges, and you know, they're 5 tests of your ambition and your courage. Are you going to take the ambitious choice along these branch points, the virtuous choice perhaps? But so I'm going to propose for most cases what I think is the most virtuous or ambitious choice and courageous choice. So the five challenges, the 5 extensions that we hope to achieve of traditional value iteration. So we want to move. I'm going to have a slide on each one of these, maybe in some cases 2. That'll be the whole talk. We want to bring in average reward. We want to bring in partial observability. We want to move to temporal abstraction so that we can plan at various and high levels. And of course, we want to do function approximation. And of course, we want to do stochastic transitions. So let's get into the first of these things, average reward. So here is our, well, why do we do it? The basic pattern of these slides is I'm going to say why, and then this sort of a solution on the right side. Why? Because really there are no episodes in the world, so you can't, it's silly, it's inappropriate to assume the world is episodic. Also, it's inappropriate to have a goal that involves discounting, because discounting is not compatible with approximation control. And you've probably heard me say that a number of times. You know, it's in the book. Anyway, what we want to do now is see that we can solve this problem. What we should be doing is maximizing the average reward per time step, and this is in some sense easy to do, although it hasn't actually been done before now. So here is our standard value iteration equation. We all know it, and this is the discount rate parameter. And I'm showing in red the things that are going to change. Now we're going to change from the conventional value iteration to differential value iteration. This, by the way, is a paper that Yi and Abhishek and I've been collaborating on, and we just got accepted at ICML. Finally, you've heard about it before. But this is choice number 1. Are we going to embrace the challenge of average reward? And it's straightforward to do so. All you need is to estimate the average reward per step. This is just a number, a scalar that you estimate. It's your estimate of the average reward per step. And then you compare the reward that you're expecting to get according to your model with the average reward rate and see if it's more or less. And you end up learning a differential value. The average reward rate is updated in this nice equation. I remember what's on the bottom of that screen, which I can't see anymore. It's kind of frustrating. I guess I could go back to another mode. But basically, yeah, it's kind of, no, can't even get out of this anymore. Anyway, I'm pretty sure down there at the bottom, it points out the thing in parentheses is a TD error. It's like a Bellman error. And so you just have to compute the Bellman error. You have to compute that anyway to do the first update. And so now you also use it to update your estimate of the average reward rate. Okay. Number two, partial observability. How do we go beyond the crutch of assuming the world gives us the state of the world? The environment gives us its state, because really it doesn't. Instead, it's appropriate to say that it gives you an observation, some sensory information, some data that you can use to help create a state, but you've got to create it. So we introduced this idea of a state update function, U, and it creates the state. It takes in the old state and the old action, the observation produces a new state. So like, look at this picture. Here we have the usual argument, usual framework where you're interacting with, and the world gives you states. But now the world is going to give us observations. And we're going to send those observations into our U box and our state update box. And it will take those observations together with the most recent action and the last state, and it'll produce the new state. And the cool thing about this, I mean, I haven't said how you would construct U, and there are many ways. And one way is, for example, to do the belief state update. Another way is just to like remember the last 3 observations. And another way would you use PSRs. There are many ways of doing it. And the thing I want you to note is that after you've done this, then you kind of return to the original case. Now you have, as far as the agent is concerned, he's going to receive states. These states are not Markov, but of course you can never count on them to be Markov anyway, because we're going to be using function approximation in a minute. And so, but from the perspective of the agent, we've returned it to the original case, which is a dramatic improvement over more traditional approaches, actually, which will do things like POMDPs, which we'll get into a much more complicated and different setup to handle the partial observability case. Whereas we're going to, with this shift of this point of view, allows us to keep it in the same perspective, same framework. Okay. Third big thing we have to deal. Life is only lived one step at a time. But we have to plan at higher levels. We have to plan, how to go to New York, how to run our life, what jobs to take. We also have to, just little things like how to wander from room to room, how to pick up an object. All these are really temporally abstract decisions. And to plan what we want to do, we can't think at the lowest level, because we have to act at the lowest level. So there's this big conflict between all our actions, which are at this tiny level. We want to be able to make individual muscle twitches at a very fine temporal grain, but we want to be able to think and plan at a higher level. I dwell on this because there's major research programs which have just made choices, which means they can't do this. And we have to avoid that. So our knowledge is about large-scale purposive dynamics, by which I mean things that we could do for a purpose, like even picking up an object. I might have a purpose of throwing it or drinking from it. Everything has a purpose. And so we have to be able to plan about ways of acting. And the way to do that is in the natural way nowadays is to use options, and our knowledge should be about options. And an option just means a policy and a stopping condition. And the model of an option is just like before, but now we have an extended way of behaving. So our conventional model, and again, I'm showing in red what's changed. So normally we take an action in a state, and we produce the next state, S prime, one time step later. Now we're going to take in an option, and it will produce a sample or a distribution over the state at which the option will terminate. And the reward, the reward part of the model will not just say what the one-step reward is, but it will, oh, thank you, Russ. I can see the bottom of my screen. Okay, let's just hold that there for the rest of the talk, please. So the R hat will be the sum of the rewards from the start of the option till it stops. Now, because of this, value iteration is unchanged. So no, because of this, I don't know, the amazing fact about options is they're like plug compatible with actions. This is the same equation. All I've done is I've changed A for action to O for option.
Is that a typo here, Rich?
Yeah.
Is this a typo?
Typo?
That should be an O right where my mouse is?
You expect me to see your mouse?
Oh, okay. Sorry. R hat. Well, what's the second argument of R hat?
Oh, yeah, that should be an O as well. Very good. Thank you.
Okay.
That's right. You would have an expected reward for the option and an expected transition probably to next states. Good. Good. Okay, so I don't really want to spend any time on this, but just this is a lecture you should have heard from me. One-step things are not sufficient. It's a trap to think they're sufficient. If we tried to think at the low level, the computation would be enormous and the errors would be enormous. We cannot rely on such high-quality models that we can iterate them thousands of time steps, or even probably 10 time steps outside of particular games. Okay, so options still have to be discovered. They don't come for free, and then you have to learn their options. And so let me just say a couple things about that. It doesn't change the fact that you need to think in these high-level terms, the fact that you have to discover the things to think about. So one way to discover is to pose subproblems for yourself. This is one of my favorites. And then given the subproblem, you learn to solve it using the normal learning algorithms, reinforcement learning algorithms. So now that's just one way. But once you have an option, however you came up with them, you have to learn their models, and you can learn their models like by Monte Carlo methods. Say, I started it here, I ended it there, I ended it in this state, I saw this much reward along the way. I can learn from that sample mega transition, jumpy transition, or you can use TD methods and learn, online incrementally off policy as you go along on each step. And I hope whatever's on that last line isn't too important because I can't see it. Okay, so fourth big challenge finally is we're going to do function approximation. We're going to recognize the main thing really, which is that the environment is huge. It's much bigger than our poor little agent here. He's got to confront this entire world with all these other agents and all these other planets in the universe and all the nooks and crannies of the world. The world is much, much bigger. So the agent really has no hope even of holding an estimate of the state, an accurate estimate of the state of the world, because the state of the world includes all sorts of things that there's even if they were known, they'd be too large. Okay, and now we're talking to you today about learning planning, and planning, is based on the model, and the model is massively more complex than the state of the world, because the model says if you're in this state, you do this action or option, it has to say what probability you end up in all the other states. So it's like the square complexity. And we are always at the limits. Like if we had more resources, we would put more resources into our state estimate. And so when you come to making your model, your dynamics estimate, you really are short of representational power, short of resources, and you're going to do something that's highly, highly approximate. And that's perhaps the most important thing we need to deal with. Now, of course, we have function approximation. When we imagine that with our fancy function approximation methods, we can do a lot, even if the world is complex. So let's see how this goes about. We're gonna instead of talking about the value of S, V of S, we're gonna talk about the approximate value of S, and that will be parameterized by a weight, W, a weight vector, W. So the difference there, you notice I'm changing from uppercase to lowercase because this is a random variable. This changes during the updating process. Here, V hat is actually a deterministic function, and only the weights change. Okay. Now, of course, the model also will become parametric. And here in the first equation, I have conventional value iteration, and I'm showing the parts, highlighting the parts in red that I'm going to change. So now if we go to approximate value iteration, we're going to change the weights. We're not going to change the value. But this thing in black remains the same. Okay, cool. I think I can see everything. Thanks, Russ. The thing is black is the same. So we're making, this is in fact the target, right? This is just an update. I figured out what it should be. Here, that thing that I'm updating towards becomes a target, and I move in step in that direction. So I make the error between that direction and where I am now, and then I move in the direction that will cause me to reduce the error. Okay, I'm going to increment it by a step size.
Great.
As you'll say. Good. Question?
Yeah, so did the hat on top of the R and P go away on the equation at the bottom?
They should be there.
Okay.
Good. I'm not going to make any distinction. All my R's and P's are the models. They're not realities, which are unknowable. Okay. Thanks.
Rich, can I?
Yeah.
A follow-up question is that once we're in the function approximation setting, because the state is too big, are we still going to make the assumption that the reward function and the transition dynamics that we're going to look is going to be a function of the state, and we're not going to try to approximate that? Is it?
So remember, the state here is going to be the agent state that's come from the agent state update equation. So we will have the state. We will have this. Our own state that we've constructed, the agent state constructed. So we will have it, and our model will be defined in terms of that.
Okay, that makes sense. Thank you.
Okay, so I want to focus on this equation for a while. So let's look at it and talk about its computational expense. Okay, so this operation, we call it a backup at state S. And you remember, many states have to be backed up. Like you do this update, this big equation, we're going to do it many times because we're going to do it in many states. And in principle, you even have to do it at all the states an infinite number of times. There are 2 outer loops in classical value iteration. So for this to be, well, of course, we don't really have to do all the states infinite number of times, but we're going to have to do it selectively, and we're going to have to be wise or clever about how we do it, because the better we select the states to be backed up, the more rapidly we will converge to a better approximate policy. So this process of selecting the states to back up and related things is often called search control. And I haven't come up with a better name, so I'll just use that today. We're controlling our search. We're saying, I should search at this state. I should search at that state. And by selecting the states to search at, you can get various kinds of planning, as in tree search is just a particular order in doing the backups, or it's closely related to that anyway. Okay, so this part doesn't worry me too much. Like I know, just as if we think about how we think, we know that you have to think about the right things, or you're just going to waste your time. You have to focus, and that's part of the skill of thinking, is that you have selected a good state to think about. And I'm more concerned about the loops that are inside the backup. So if you look at this equation, you see there's a max. So that's a max over all possible actions. And there's a sum. That's a sum over all possible S prime. Okay. So we got 2, and those are nested. Right? If you look at the picture, it's kind of obvious. We have many actions we're looking at, and then for each one, there are many possible next states. And yeah, many possible. Here there's 2, but really there's going to be many. So those 2, let's talk about those 2 inner loops. The max could be a problem if you have lots and lots of options, but I can see how it could be done incrementally. Probably you can too. Like you don't have to really do all the actions. So maybe some of the actions are really poor, and you've learned that you don't need to re-update them all the time just to find out that they're not the best. So a simple strategy is for each state, or in a function approximator for each state, you store what you think is the best option, and maybe what you think is the best value you would expect to get for that option, yeah. And then when you consider a particular state in action, you just see if the action you're considering is better than what you expected. And if it's better, then you update things. And if it's not better, you just keep going. So you can do this, the max, you can do incrementally. Now the sum is more of a problem if the world is stochastic, and And there's something very important that I want to say there on the next line. But the
You can see
basic
my
thing
screen.
is that we want to focus on the on this part here. This is inside the sum. This is the inner sum, the inner loop, and it's going to rule the computational complexity of everything. And so, and it looks scary. So that's actually the fifth and final challenge. That is to handle stochastic worlds and to not use the crutch of determinism, which actually, if you look at the literature, is very often used. So obviously, of course, we use it for things like chess and Go. This is our expected value computation. This is the sum that is in the inner loop that we have to do it quickly. Now, you notice it's cheap if the world is deterministic. If the world is deterministic, then there's really only one S prime that has probability 1 and everything else has probability 0. And so you can reduce the sum to just accessing that one value. The world is, of course, extremely stochastic. You do an action, and even the very next thing is going to be uncertain. And the world has such an enormous state space that really there's lots of little variations for everything you're going to do that you are only going to capture. That you need to handle somehow. We need to have a planning method that will be scalable and general and gracefully degrade as we handle more and more complex worlds. Okay, so another case that's simple is if the world returns samples of the next state, because then you would just use the sample times the sample's value, and then you'd have a quantity whose expectation would be equal to this sum. But samples, then you'd have to do multiple samples and average over them, and that involves computational expense. And there's also the difficulty of getting a sample model, which I'll talk about at some point. Okay, so there's a trick. There is a trick that you've heard about before, and the trick is if the value function is linear. And so this is the proof that the trick works. But first, I guess I should go here. The conventional model is the trick is what I call an expectation model. And the expectation model, instead of, we give it a state, and normally we expect a probability distribution over the next state, but here we're going to give it a state, and we're going to get an expectation of that next feature vector for the state. Now, another little thing you notice is that I'm writing the state in a different way. Here it's just a state. It could be a discrete thing. It could be a finite number of them. But now we're going to talk about expectation over states. So they have to be real numbers or real vectors. So, and because when we do function approximation, we generally want them to be real vectors anyway. So let's take them as real vectors, and we're going to produce an expectation of the next real vector. And you can show, remember, this is the quantity we want to compute cheaply. And given that this value function is linear, we can write it like this. And then by grouping things, we can group the state with the sum. We can pull the W outside the sum, right? Because it's not involved in anything inside. And then we have a final equation somewhere down here that says that notes that this thing in parentheses, just look at it. It's an expectation. It's like I'm summing how likely is each. There should be an S prime here. You notice there's an S prime there. Should be an S prime here. So this is like the expected next state. I'm summing over all those possible values, multiplying times the feature vector for that state. And so this is an expectation. That's the next line says. And then S bar is going to be our expectation. So when we produce the expected next state, that's S bar. Our model, expectation model, will produce that. And then we can do this whole thing directly. And the expectation model is deterministic, and it just produces the thing that we need to dot with the weight vector. And we've done this stochastic thing very cheaply. Okay, so I'm sort of wrapping up now. So there's some questions that you probably have, like, does this trick work with all the other things mixed in, options and average reward and the state update? And yes, it does go through. I've tried to consider the simpler case in this talk, just so not to introduce an unnecessary complexity, but everything goes through. Now, you're undoubtedly you're also worried about using linearity, because that sounds like a restriction, and I've explicitly said my goal is generality and scalability, and I think this is not clear. I think it might not be a problem because we need some way of gradually moderating our how much detail we get and we try to represent in our model. And one way to do that is by adding features. And by adding features, you can, of course, make everything linear. You can approach linearity as you add more and more features. And so the choice of making things linear doesn't make things impossible, but it does put more burden on the feature constructing process. Okay, so that's how that's being traded off. And so, you know, the other alternative, which is feasible, which might be feasible, is to learn sample models. And the problem is I have no idea, and if I don't, then probably no one does. I have no idea how to learn a sample model with options, given that, you know, these things could terminate at various times, and how you would do that, even in a Monte Carlo way. So can we make this work at all? I don't know. Okay, so this is let's close then with my best guess, or I get one more slide. My best guess, a vision of a full solution to planning, and my best guess is that we try to make this work with the expectation models, with the linear value function, and with creating state features. But this model is going to have to be heavily annotated with, quote, metadata. As we don't have just the expectations, we have some measures of how certain we are of them, how confident we're going to be in the results, how useful this element of the model has been in the past and is likely to be in the future. Now, remember, we already need this. Like, we're going to have usefulness measures when we do search control. I think this way of thinking is leading me to more and more think we're going to be doing this heavily. It'll all be heavily annotated. So useful options are rare. The agent searches for them. Because of this, learning the model is not like filling in a table, or learning knowledge about the world is not like filling in a table or estimating, you know, known things. It's more like searching around, looking for the gold, looking for the good things, rather than just filling in things in. So the goal here is options whose approximate models are useful. So options provide the semantics, and they make the learning problem well-defined, but then we still have to find the useful models, and that involves discovery, and that part is still open, as well as being at the bottom of my screen. So take-home messages: planning is subtle and surprisingly unsolved, particularly if there are stochastic dynamics. There are these grand research strategy decision points about planning. They are important. We should be aware of them. You don't have to make the choices, the branches I've chosen, but you have to choose. You should be aware of the implications. This is a grand quest. We're talking about the automated discovery of knowledge. How we should think about the world, and how we can use that to think and reason and plan. So we should be ambitious in our vision and incremental in our progress. Thank you very much.
Thank you, Rich. So we are opening the floor to questions now.
Whew. I was even later than I thought I might be. I'm sure we'll allow people to ask a few questions, even though I've run over. What else can we do?
I have a question, Rich. So when you showed this diagram with a state update, then you kept the state update function outside of the agent.
Yeah. Oh, no,
Is
not
there-
outside. Oh, I did. You're right. I did. That's a mistake. The state update thing is
All right.
inside the agent. Good.
Great. And then second question is, when you are doing value iteration with function approximation, the update rule that you showed, do we know whether it's going to be stable?
No, I want to just say no.
All
I think it all depends. It depends on many things. We don't know.
Right.
Yeah.
Thanks.
Good.
By the way, Rich, the Zoom thing is my fault. Sheila asked me which one to use. My understanding was that people are having a lot more trouble with Google Meet. And our meeting, I saw that you presented something to me using Zoom. I thought it would be fine.
Okay.
I'm sorry. That took so long.
Okay. Are there any more questions from anyone?
Yeah. I was just wondering if you could maybe go into your further thoughts on sample models with options. Like, so I'm just sort of imagining a rollout, right? And I think that would be easy, but I haven't tried it nearly as much as you have. So,
Well, the first thing to note is to do it in a rollout way, you're doing it in an on-policy way. You have to commit to the option and take it through to the end, so you can know here's a sample of what the option would do in that state. Yeah, what I would really like is to be able to learn off-policy, and so I think I don't know how to learn. I don't have any clue how one would learn off-policy in a sample-based way.
Rich, do you think is your struggle because you're not sure how would you learn a distribution from samples? Because it does feel like if I had a sample-based model, could I do the same bootstrapping that I take one action consistent with the option. I could then ask for a sample from my option model in that new state, and that could be a sample of my option model for the previous state. And now it's a question of like some way to train that it's a little bit unclear, but like it doesn't feel so. I can't see why you're so adamant that it doesn't work.
Well, I'm not adamant in the sense that I would really like to have a method that was a sample-based method, because then I can make incremental progress by comparing that method to the expectation method, and just do science and figure out which method works best. I'm really just been scratching my head to find anything that I could even convince that I can imagine would be general purpose for a sample method. Given, it's really important that I didn't dwell as long as I'd hoped. Genuine approximation means that the world is never accurately known, because the world's much more complex to us. There's so many works, including, the original Dyna work, which only dealt with worlds that were much smaller than the agent. So there are sample-based methods that are of that nature, that say, in the limit, we know this method will reach the true thing, and then you can make statements about its abilities. But if you are genuine approximation, you can never become correct. Anyway, it could just be me. I would really like if someone would tell me how to do it, so that I could team up with that person and run experiments and do the comparisons. Yeah.
Okay, Rich, we have a question in the chat. Does the expectation model by design assume unimodal dynamics in some sense, or does it just depend on the representation type?
It doesn't assume that the model is of any sort. I mean, that it's dynamic. So the world has any sort of dynamics. The world can easily be nonlinear. Michael and Albors and I and one other person, maybe it was Chaba, I don't know, wrote a paper where we assumed the world on the special case when the dynamics of the world are linear. And but the expectation model is just that you get an expectation. The dynamics do not have to be linear.
Okay, and we have one more question. So the focus should be, so the focus should learn rich enough features that can be used in a linear way.
I don't know if I want to say the focus. That will be one of the things that will be important. Well, okay, so there's the discovery of the features and there's the discovery of the options. One could leave out the discovery of the options and, just for the moment. And then you would have just the whole focus would be on the discovery of features that would enable approximately linear value functions.
Okay, and we'll just allow for one more question. Amir.
Right, yeah, hi, Rich. So my question is that about I guess one way to think about whole model-based RL is that we see different modules, like a module that learn the module that do the planning. But then one question is that, well, our model is never going to be completely accurate. It's just an approximation of the world.
Right.
But our planning methods kind of think that the model is actually the real environment. We are using the same, say, value iteration that was designed for MDP, but now we are not dealing with MDP anymore. So do you think we somehow need to kind of consider the interaction of inaccuracy in the model and maybe modify the planning methods, maybe make them somehow robust to possibility of error?
Yes, exactly. The planning method cannot just take the model as given. There's going to be a strong interaction. That's what I was sort of trying to say with the annotations on the model for utility. And yeah, I think that's going to be the key. Good. Thank you, Amir Masood.